Let's go to section 1.4. It's about unit consistency and unit conversions. So as I mentioned before, from the base quantities, we can create so-called derived quantities, like volume. A volume is expressed in terms of length to the third power. A width times a height times a length is how you would measure the volume, calculate the volume of a rectangular box, for example. Acceleration is a length divided by a time squared, it turns out. We'll be seeing that soon enough. Now, it's critical that you get the habit of keeping the units in your calculations, because it provides a diagnostic check for mistakes. A bad attitude about units is, I know what the units are going to come out to be at the end, so I'll just throw in the numbers without units, do the calculation, at the end I tack on the appropriate unit. Yes, that's possible if you never make mistakes. A much better approach is to keep track of the units and make sure that the units do come out to be what you think they should be at the end. For example, if you're figuring out the mass of the elephant and you find that it's 15 seconds, it means you've made a mistake, and you should go and find the mistake. Don't just write 15 kilograms and go on. Now, here's an important point about unit consistency. We can only compare, add, subtract quantities having the same dimensions. So this provides another cross-check in some situations. What I mean is, it doesn't make sense to ask which is larger, 2 kilograms or 25 seconds. We can't compare things that have different dimensions. It doesn't make sense to add together 15 kilograms and 45 seconds. That never happens in physics because the result has no physical interpretation. So if you do a calculation and you find that you're supposed to add together two quantities that have different dimensions, it means you've made a mistake, and you should go back and find the mistake. Of course, it's okay to add together 1 foot plus 1 inch. Those are both lengths. They just happen to have different units. I'm talking about adding together or subtracting quantities that are of entirely different nature altogether. It's just not possible in any meaningful way in physics. It doesn't happen in physics. Now, maybe this is obvious, but I'm going to talk about it anyway. When we add together quantities like 2 hours plus 1 hour, well, 2 plus 1 is 3, but what are the units of the result? It's hours as well. When you're adding together quantities, you should put them into the same units first, and then you can just copy the unit over to the answer. When you're subtracting, the situation is very similar. 200 grams minus 100 grams. You do 200 minus 100, and then You have to get the units to be the same before you make the subtraction. They're both grams. The result would be in grams also. Adding and subtracting are like that, but multiplying is different. If I take 3 inches times 5 inches, why would we do that? Why would you ever want to take 3 inches times 5 inches? That would be a way to find the surface area of your index card. Multiply the width times the length. The unit of the result is inches squared. You have to multiply the units. This is an area. Divide. Suppose I wanted to divide 22 centimeters by 7 centimeters. 22 divided by 7 is about 3.1. Why would I ever want to divide 22 centimeters by 7 centimeters? One possible answer is I want to figure out pi. I measured the circumference of a circle, 22 centimeters, and I measured the diameter, 7 centimeters. The result has no units. The units are as if they were multiplying the numbers, 22 times centimeters divided by the quantity 7 times centimeters, and the centimeters cancel in the calculation. Another possible reason for this calculation is you've got 22 centimeters worth of wood and you're cutting it into 7 centimeter lengths and you want to know how many pieces you can cut. The number of pieces you can cut wouldn't have any units. It would be 3 plus a little bit left over.